Why should we do research? Because as humans, we are interested, we divide the events that are occurring around us into neutral, painful, or pleasurable. And all the time, from birth to death, we are seeking to avoid the painful and seek the pleasurable. So, any event that can cause pain or pleasure is event of interest. In the sense of health, a normal converting to diseased, a disease getting cured, disabled, or dead, all these are transitions which are events of interest. And the arrows represent transition rates. And we'll talk about these transition rates. So, how many out of how many are transiting from stage A to B? For example, 50 out of 1000 are becoming blind per year. This is also called as incidence rate or event rate or transition rate. Understand this transition by understanding this jar. This jar is a 1000 cc jar which is filling at the rate of 2 cc per minute. It has 10 cc's of fluid initially and it's emptying at 1 cc per minute. So we can ask you, in how much time will there be 20 cc of water in the jar? Formula is volume at time t is equal to volume at time 0 plus time into filling rate minus emptying rate. That means 1 cc per minute filling, 2 cc minus 1 cc. And if you want to get 20 cc from 10 cc, that means you need 10 cc's more of fluid. So it will take 10 minutes to become 20 cc. If you use this formula, convert cc's into persons, then prevalence of a problem or disease at time t will be equal to prevalence at time 0 plus time into incidence rate minus attrition rate. Attrition rate, why attrition? Because either the person is cured, dead, or migrated, lost to follower. Therefore, if there were 10 blind people in 1000 people village, 2 were becoming blind per 2 years and 1 was becoming cured per 2 years by the cataract surgeon, then how much time would it take for the number of blind to be 20 in that 1000 person village? So PT is equal to P0 plus T into incidence rate minus attrition rate. Convert it into numbers and you would be able to calculate T. 10 units of 2 years. That is 5 years will be the time taken. Now this incidence minus attrition rate is not constant over time. And therefore, you have this survival curve which denotes the variation in the transition rate. For example, if there were 100 people who had malignancy and 10 died the first year, 5 died the next year, 5 the third year, and 3 the fourth year, then this curve tells you that the probability of dying in the first year was 10 out of 100. But the probability of dying in the second year was 5 out of 90, because 90 were at the risk of dying in the second year. Survival is the chance of surviving the first year is 90 upon 100. The chance of surviving the second year are 85 out of 90. So another concept in this is that supposing in the second year 3 were lost to follow-up. So these are the death rates and these are the surviving rates. So I say supposing in the third year 2 persons were lost to follow-up. Then in the third year, chance of surviving will be 8. The denominator will be 83 because you have followed up 83 patients only. And therefore the denominator would decrease, and you will have that the chance of surviving the third year is 80 out of 83 instead of 80 out of 85. This being able to take care of loss to follow up is called as censoring. At the fourth year end, there were 77 patients. 33 died in the 4 years. So the death rate is 33 upon 4, that means equal to 8.2 per year. So that is the incidence rate. But the cumulative incidence is how many were surviving, what proportion was surviving at the 5 year. So the time to which 50% survive is called as median survival, and the proportion surviving at the end of 5 years is called as 5-year survival. So if I say that 33% were surviving at the end of 5 years, it means 33% is 5-year survival. So what have you learnt? You have learnt incidence rate, you have learnt cumulative incidence, you have learnt attrition rate, you have learnt prevalence, you have learnt formula relating to prevalence, PT to P0, using incidence rate and attrition rate. And attrition is due to death, cure or migration. That's what you learned. Next you learnt the survival probability over segments of time, how to deal with loss to follow up by censoring. You learnt cumulative incidence, that means 5-year survival, and the difference between cumulative incidence and incidence rate. Now we see how we relate causal factors having the power to alter the transition rates. Or when will that event of interest occur? Duration at which the event of interest will occur. So we are now starting to compare treatment A and B for retinoblastoma, and we have drawn these two curves. In the second year, you see that in the A group 90 survived out of 100, and in the B group 80 survived. So you get this 2/2 table. With treatment A, 90 survived, 10 died out of 100. In the B group, 80 survived, 20 died out of 100 that you began with. So the risk of the probability of surviving in this year with treatment A is 90 upon 100, with treatment B is 80 upon 100. Therefore, risk ratio is 90 upon 100 divided by 80 upon 100. The odds of surviving is 90 out of 10, 90 upon 10, because here the denominator does not contain the numerator in odds. Therefore, with treatment A it is 90 upon 10, with treatment B it is 80 upon 20, and therefore the odds ratio is 90 upon 10 divided by 80 upon 20. Use such a table to calculate the risk ratio and odds ratio over the years 1, 2, 3, 4 and 5, and then using EpiInfo you get an adjusted odds ratio for time. You can combine all these tables and you get the Mantel-Hansel adjusted odds or risk ratios which has been adjusted over time. Finally, one concept that you did not reach this point, from this point, and on 31st of December of the first year. It must have been a gradual step-by-step curve. So this curve, which denotes the actual point of time at which the event occurred, is called as actuarial survival curve. This curve, where time is categorized into 1 year, 2 year, 3 year, and it does not take into consideration that gradual transition, is called as Kaplan-Meier survival curve. So we have learned to relate cause, the type of treatment, to the time distribution of event of interest, that is survival. And this cause can be type of treatment, it can be grade of tumor, it can be any other prognostic factor or etiological factor. But if causes are multiple, like we want to correlate age, sex, type of tumor, stage, and then causal relation is quantified by what is called as Cox proportionate hazard model. Survival is equal to beta 0, some sort of constant, beta 1 x1 plus beta 2 x2 up to beta n xn, where x1, x2, x3 are all the factors that are causing difference in the transition rate or causal factors. And here the ratio beta here the factor beta 1 will be linking x1 to survival, keeping all other factors constant. And if you take the exponential of beta, you will get the adjusted odds ratios of beta 1 of x1 to survival, keeping all other factors constant. You can use EpiInfo to do this.